All right, just to let you know, the lecture is being recorded. Good morning, everyone. Again, this is essentially our last proper lecture because next week, as I explained in the um, we're going to have a revision session. We won't have any workshop next week. In the revision session, I will explain you what is the format of the exam, and I will give you a mock exam, essentially some questions that or the questions that you may see in the exam. I mean, not you may see, similar questions, obviously. This is our last content-based lecture that we have, and then after that, you don't have to see me unless you choose to in the second term. So let's get started. So we started nonlinear programming last week. So I showed you um, what models or mathematical formulations or nonlinear programs, essentially, if you have any of the functions in the model, either the objective function or any of the constraints being nonlinear, this causes our model to become nonlinear programming. It is important for us to know because accordingly we can choose a proper approach to solve the problem. And on top of that, I told you we can find out if a function is convex or not. If the function is convex, that's a good sign that we will see today, because if you have a convex function, you know that there is a single point which is your global optima, and you'll just, whenever you found that point which satisfies a certain sort of criteria that we will cover today, you will stop and tell that, oh, found the optimal solution. This is whereas other functions, if the function is not convex and it's not concave for a maximization problem, then we are in trouble because there are similar points which share a similar set of similar features that you think that they might be the global optimum, but they are not. So today we are going to see what are those features or similarities that I'm mentioning here. But before that, let's start with an example of nonlinear programming. Where do we see nonlinear programming? I told you this highly depends on the context of the problem that you're dealing with. That it forces you to have a nonlinear objective function or nonlinear constraints as the function. This is a very well-known problem, nonlinear model that we have, data fitting. This is one of the applications of nonlinear programming. And at the end of this session or in the workshops this week, I will solve a few questions that you have to model the problem as a nonlinear program, because otherwise the problem forces this. This is data fitting, where what we want to do here is to we have to pay pen. So what we have here is there are some observations that we have. These are the observations, some data that we have, and then we want to predict what can be the next observation. So what we have here, that we have x-axis and y-axis. These are the points that we have, which are these blue ones, or the observations that we have, and this is our prediction. Obviously, you want to have the prediction. The best prediction that you could have is a line which through all of these points, right? Which is not possible. Because if you do that, you know that exactly you found the same, but it's not possible. So what we do here is we want to find this line here, this red line, which is, I guess I need my charger, sorry, because I need my laptop for the whole afternoon. So let me just plug it into the so what we want to find here is we want to find a line which is the closest to the points that we have. Okay, now I lost the screen. Okay, it is back. Okay, fantastic. So we want to find a line which is the closest to all points that we have. So you can see the distance of this point to the line is this one. The distance is this one. This is this one. This is this one. These are the distances of the real observations and what we predicted, which are essentially the errors of what we found. Okay, hello. For example, let's say the problem is this, the observations that we have. In order to study the effect of a certain medication on a patient, blood samples are drawn at certain times after the patient takes a dose of this med to measure the concentration of the medication in each sample in the blood. The concentration is Yj at time Tj of each sample is recorded, and J can be from 1 to M, so M different samples that we have. The following function, G of X and T, provides a good prediction of the concentration at time T for appropriate values of the two-dimensional parameter vector of X1 and X2. So what we have here is we have patient, we have the blood, we have the medication which is applied, and we have samples to see what is the concentration in the blood. So sometimes when you apply more medication, the concentration is higher. When you want to find what is the best amount of medication which should be injected or should be applied to the patient. So you want to predict if this is the dose, how much concentration will be, and accordingly you want to optimize the amount of medication which should be applied to the patient. So G of xt is given to us. This is something that is given to us as is x1 plus tx2. This is the two-dimensional parameter that we have. So x1 and x2 are the vector that we have. G of x t at different times provides a good prediction of the concentration at time t. So we want to see at time t what will be the concentration. Essentially, this is what we want to. There are some observations that we have now. At some points here, we want to see if this is the amount that we have, what is the concentration, what will be the concentration, which is a good practice to see how much we are going to apply to the patient. Okay, find the parameter vector x so that this model best agrees with the observations by minimizing the following least squares function. This is what we want to do. So what we have here, we want to minimize this function, which is the least, essentially this is the squares of the errors that we have. This is the prediction that we have. Yj was given to us, which is the concentration at time tj. So these are our observation that we have. This is the observation that we have. This is the prediction. This is the observation. This is the prediction. What we want to do here is we want to minimize these errors that we have, the distance of these observations, because this is the observation that we have and this is the prediction. We want to find a prediction. We want to find a g of x and t. Essentially, we want to find these two, the vector that we have, so that the error is minimized. How we are minimizing the error? It is the least squares of errors. So for each of them, it is the prediction that we have minus observation squared. This is the first one. We have the second one. We have the third one. It goes until we have the mth prediction at time tm and observation at time tm. If we know this, we have the function in a way that the minimum error happens and we can predict what will happen in the future. As you can see here, it is simply can be seen that this is a nonlinear model that we have. Okay. Oops. Okay. Did you hear Vince? That's interesting. Okay. Okay. I don't want to hear that, but funny enough, it remains on a slide from years ago. So I will keep it in this way because I don't know how to disable the annotation. Okay. So Unconstrained optimization, we talked about that there is nothing to limit the value of the decision variable. So what we have here is the function that we have. This is our function which we are trying to minimize, and you can see here that x is can be any value in the n-dimensional space, and it can be a real value. We talked about this. And x we have here is the vector of all decision variables that we have. So essentially we can write it as a vector or list, let's call it whatsoever that you want to call it, x1 to xn, which are our n decision variables we have. There is no constraint that we have imposed on x, our decision variable. Remember that this function is a convex function because you can find 2 points in which the connection segment is not above the function. And remember, being above is the value that you get from the line is greater than or equal to the value that you will get from the function for the same value of x. This is another one that we have, unconstrained optimization problem, which is let me see if there is any. Okay, there is nothing here. That's good. This is another function that we have. It is nonlinear, obviously, as you can see. As we discussed here, there are like 2 points that we have, and they have similar features. This is what we discussed last week. And we said that solving this problem is harder than this one, because in the previous one there is only 1 point that you have, you know, the function is convex, and if the function is convex, you know that there is a global optimum, and if there is a global optimum that you have, you will immediately stop. This is whereas this one, where you have this point, and you can see that, as I told you, it's like something like that you're reducing the value of the objective function until here, and now it goes up. So you think that there is here that you have sort of like value. And if you don't get lucky, you may just think, oh, this is the one that I found, but this is not, because you can see easily that the optimal solution is here. What do we call this point? Do you remember from last week? What do we call this point and this point? What do we call them? The left one is local optimum, this is local, and this one is global optimum. Fantastic. Local optimum, remember that what we said is local optimum is a value that you will get. This is the minimum with respect to some neighborhood. Essentially, there exists a neighborhood on both sides of this value where this point is the minimum. This one is a minimum for the whole space or domain of the decision variable that we have. This one, which is global optimum, at the same time it is local optimum, because if it is for the whole domain of the decision variable, it is for a neighborhood as well. This one is only a local optimum. Local optimum is not global optimum, but global optimum is always a local optimum. Now, if formally we see the definition of neighborhood, we should write it in this way. So what we have here, this is another point that we have. X2 is this point, and this is X1. Obviously, we can see here that X1 is a local optimum, while X2 is the global optimum. X1 is local optimum because there exists a neighborhood on both sides of this decision variable, so that this point is the minimum for the neighborhood, while this one, that neighborhood is the whole domain of the decision variable that we have. Now, neighborhood itself is written as epsilon. Epsilon can be a very small value or a big value. It doesn't really matter. So what you can see here is that x1 is minimum in the neighborhood of x1 minus epsilon 2 x1 plus epsilon. Okay, and we can see that this value of f of x1 is less than or equal to the value of f x1 minus epsilon and f x1 plus epsilon. And for any value x within this neighborhood, what you will get is between f of this one and f of this one, and still you can see that f of x1 itself is less than both, I mean any value that you will get in between these two. So it is the local optimum that we have. This is the minimization problem that we have. So this essentially, this is what you know from last week, and as I asked, and you can see that you guys all know that this is local and this is global. Now you know the formal definition. If you want to express that a point is the local optimum, you have to write this. There exists a neighborhood epsilon in which any values x in between them will have a higher value compared to this local minimum point that we have. It should be greater than or equal to this value. So you may have a function like this, for instance. Wanted this to be a bit lower. So let me just erase this and let me get back to this. So the function that you have is, oops, like this. Okay. Okay, accepted. This is the global optimum. Obviously you can see, and there is a point like this, and if this was straight, there is a neighborhood here in which this point has a value function f of x1 which is less than or equal, it is equal to all values in the neighborhood. Okay, this is still a local optimum, whereas this one is global optimum. How many local optimum we have here in this specific example? How many? What do you think? How many local optimum we have here? Local minimum we have? Infinite, because all points on this line are local optimum, because you can define a neighborhood for this specific, for each of these points that you will find on this line, in which the value function of those points is always less than or equal to the values of the neighborhood points that you have. Okay, good. So a minimization problem can be written as this: minimization of fx1 where there is no constraint imposed on x, because x can be any real value in the n-dimensional space that we have. Global optimum or minimum is the best solution x star in terms of the objective function, which means that f of x1 is always less than or equal to f of x, all values of x, where x is in n-dimensional space. Now, local optimum or minimum is the best solution with the neighborhood in terms of the objective function. Here we can write it in this way: neighborhoods given parameter which epsilon is greater than 0, it should be a strictly positive, and then we define our neighborhood as x minus epsilon to x plus epsilon. So this is the point that we have, and here is the neighborhood that we have. F of this x bar or whatsoever is always less than or equal to f of x, where x belongs to x bar minus epsilon to x bar plus epsilon. Okay, including them. So it is a bracket here, square bracket that we have. So as you can see here, f of x star is always less than or equal to all values of x, I mean the value function with the domain of the decision variable y. For a local optimum, we have to be able to introduce a neighborhood in which the value of this point is less than or equal to the values of all other points within the neighborhood. So here we can see that for a global minimum x star, f of x star is always less than or equal to f of x for all x. For a local minimum x bar, there exists an strictly positive epsilon such that f of x bar is less than or equal to f of x, where x belongs to the neighborhood. This is the notation that we will use for neighborhood. Neighborhood of x bar within epsilon. Okay, this is what we can see on the graph here. So these 2 points here, as you can see, if you have a convex function like f being x squared, this point is obviously our global optimum, because we know this is convex. And whenever you come to this point, you just stop and say that, oh, I found the global optimum. This is, whereas this one, we have similar points like this one, where both are, one of them is local optimum, the other one is global optimum, and you sometimes get unlucky, and there are lots of hundreds of them that you have, and you have to draw all of them to find the global optimum. So here for convex function, local and global optimum are the same. In these ones, it is really easy to see where is the global optimum, okay? But there are certain cases in like one-dimensional space, two-dimensional space, you can visualize them to see them. If you don't have them, you can use online tools to visualize the function and see how they look like. But in more dimensional spaces, like three-dimensional, how you can find the global optimum or the local optimum. For instance, this one, how do you see where is the local or global optimum? This is an example of unconstrained optimization, again, where we are minimizing fx. Fx is a function which looks like this. If you visualize it and there is no constraint imposed on the value of decision variable. Now we want to find the local or global optimum. So as I said, we want to find the values x1, x2, I mean the x vector, which is the whole decision variables that we have with no constraint imposed on x. Now, necessary optimality conditions. So do you remember that I said that there are points that they share some sort of like similarities, some features, and when you see them, you say that, oh, I have a local optimum or I have a global optimum. For a convex function, you know that if you have this point which has these features, then you can stop because you know the local optimum is global optimum for a convex function. This is whereas a non-convex function that you have, you can't say that. So these features that I mentioned earlier is necessary optimality conditions, the first one. Assume that we have this function fx that we want to minimize it and there is no constraint imposed on the value of the decision variables. We have first order necessary optimality condition. So we have first order, second order necessary optimality condition, and then we have sufficient optimality condition that we will discuss in the next slide. First order necessary condition. That's the first one that we want to discuss, which is the raise D. It says that suppose that f is differentiable at some points x bar. If x bar is a local minimum, then the first derivative of the function, if you plug x bar, it is x bar. I have to change that. With respect to x, should be equal to 0. Okay? So if I go back to this example here, it's fx is x squared. Okay? The first derivative of this function is 2x. Okay? Now it says that if you plug in the value of this point x bar, which is 0 for us, f prime of x is equal to 2x. If you plug 0 in, you will get 0, which is this point, which means that the gradient is equal to 0. The first order optimality condition here, necessary optimality condition, says that if you take the first derivative and you plug in this x bar and it is equal to 0, then this point is a local minimum. This is what it says. Okay? If it is differentiable, you take the first derivative, just make this, if this point that you have makes the first derivative equal to 0, then it is a local minimum. This is what it says. The second order necessary optimality condition says that suppose that f is a twice differentiable function at x bar. If x bar is a local minimum, then the first derivative for this point is equal to 0. The second derivative is non-negative. Do you remember that? If the function is, if the second derivative is non-negative, we call the function as a what? We call it the convex function, right? Non-negative. This is what we covered last week. Okay. Now keep this in mind. Okay. The first order says that the first derivative is equal to 0 for that point. That's a local minimum. Then the second order optimality condition, necessary optimality condition, says that if the first derivative is equal to 0 and the second derivative is non-negative, if that's the local minimum, the first derivative is equal to 0, the second derivative is non-negative. Okay. Now let's assume that x is set of all local minima. Set of all local minima. You may have a function which looks like this. Okay, so you can see this is a local minimum, 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 this is also a local minimum, this is the global minimum, right? This is also a local minimum at the same time. Okay, that's why you may have many a local minimum. And this is what I said. This is this can be a problem that we have too many of them. So let's assume that X is set of all these local minimum that we have. O1 is all x's that the first derivative is equal to 0. Okay? It says that the first derivative is equal to 0. Are these x and O1 the same? Do you think that x and O1, these two are the same? What do you think? Do you think these two are the same? Set of all local minimum that we have, and we have some x's in which the first derivative is equal to 0. Are these the same? What do you think? Remember in the previous slide, we have two of them. First, it should be equal to 0. Second, this should be also be non-negative. So I have one comment. No, x is a subset of O. Very good. What we have here is just the first derivative becomes equal to 0. I'll show you an example. You may have this function, which is x cubed, f x equal to x cubed. Okay, this point that you have here, I didn't write it draw it properly. The derivative at this point is equal to 0, but you can obviously see that it's not a local minimum. Okay, so it's not enough to have this. This is the necessary condition that we have, the first order and the second order, and then we have a sufficient condition as well. So O1 is set of all decision variables that we have, all points essentially, the values for the decision variables, that the first derivative is equal to 0. This is x, local minimum that we have, and this is O1. So as Oak said, x is a subset of O1. Okay? Okay? And it just showed you with an example that there are points that you have that we call them stationary points, that the first derivative is equal to 0, but they are not local minimum. Now, we have another one now. O2 is set of all decision variables that the first derivative is equal to 0, and the second derivative is greater than or equal to 0. Where do you think O2 is? Is O2 inside of X? I mean, O2 is a subset of X. It's a subset of O1, or is just includes everything, X and O1. What do you think? O2 is set of all decision variables where the first derivative is equal to 0 and the second derivative is non-negative. What do you think? O2 comes here. It's a subset of O1 because you're narrowing down. Okay? And it is greater than X because it's not enough for us to have the local optimum. Now, this was the first, these were essentially the necessary conditions that we have, necessary optimality conditions, and we're talking about optimal solutions, right? And we said that X is the set of all local minimums that we have. O1 was those with the first derivative is equal to 0, and then we had O1 where X is the local minimum. O1 is set of all values that makes the first derivative equal to 0. Now I have the second derivative be non-negative. Okay, it can be non-strictly positive as well. That we'll discuss it now. That's why O2 is a subset of O1, but still local minimum or a subset of O2. Now we have the sufficient optimality condition. Second order sufficient optimality condition. Suppose that f is a twice differentiable function at x bar. If the first derivative is equal to 0 and the second derivative is strictly positive, then x bar is the local minimum. Okay? That's why you see here that these two are different. O2 and X are different from each other. The second order sufficient optimality condition says that if the first order, if the first derivative is equal to 0, and then the second derivative is strictly positive, then those values that make the first derivative equal to 0 and the second derivative is strictly positive become local minimum. We have this now, O3. O3 is set of all decision variables that we have in Rn, where the first derivative is equal to 0 and the second derivative is strictly positive. It's not greater than or equal to 0, but it is greater than 0. Look what we had here. It wasn't like flat. This is what we have. Do you remember that I always told you that this convex function looks like a cup, where the bottom is sharp, so there is a single point that you will see. That's why this is greater than 0 that we have here. So O3 is here that we have essentially all global optimal solutions that we have for the problem. So we started with the local optimum. We know that global optimum will be among the local minimums, right? Because global optima itself is a local minimum or local optima. So among the local optima that we have, one or some of them become the global optima. That's why O3 here, which is the optimal solution that we have, it is a subset of local optima. Okay? Do you have any questions for me until this point? Any questions? No? Do you want me to repeat this? Okay. So let me go back. Let me clear all the writings. That's easier. Okay. So what we are trying to do here is we want to find the optimal solution. Okay. The global optimum. We're talking about optimality conditions, so we are looking for optimal solutions. And at this point, let me go to the yes. And at this point, we're talking about the conditions which gives us essentially, if you have these conditions, we can say that this point is the global optimum, or this is the optimal solution for any function like this. Still, this is an easy one to see because you visualize it, you can see how it works. But there are like multi-dimensional spaces that we have. The number of decision variables are higher, and then it's not really possible to see how it looks like to find the optimal solution. Okay. Therefore, what we do here is this is exactly what we did in convexity as well. In discussion with convexity, we said that sometimes you can visualize the function, you can see them, you can easily see visually that this is a convex function or not. But we said in most of the instances you can't do that, therefore you have to be able to prove it using the definition. That's the same. You have the function. Now there are different points that you have that they can become the local optima. Among them, some of them become, or one of them becomes the global optima. There are cases that you may have more than one global optima, right? In nonlinear programming, it can be 2, it can be 3 of them, or whatsoever. Now, if you have two conditions here, the first one is necessary condition, and then we have sufficient conditions. The necessary condition, optimality conditions, are two orders, the first order and the second order. So what we are trying to do is we're narrowing down different points that we can have. Okay, we start from the ones that I showed you. It can be stationary point where the gradient is equal to 0. Among them, some of them become local optimum. Among the local optimum, one of them, some of them become global optimum. This is what we are trying to do. That's why we wrote O1, O2, and O3, and we had X as well at the beginning. Okay, the first order necessarily optimality condition says that if a function f is differentiable, which is really important, at some point x bar. If x bar is a local minimum, then the first derivative for this specific point x bar should be equal to 0. Okay, so you just take the first derivative, make it equal to 0, find those x's, x bars, that make the function equal to 0. I mean, makes the first derivative equal to 0. This is first order necessary condition. It's not enough here to stop. The second order says that suppose that f is a twice differentiable function at x bar. If x bar is a local minimum, then not only the first derivative is equal to 0, but also the second derivative is non-negative. Okay? We'll come to that point in the next, after I finish this one, we'll come to the convexity and global local minimum. Okay, so why we have the second order? Because I showed you this example that you have. This is you may have something that's really awful what I draw, but here there is a point that you have, and the first derivative is equal to 0. Remember that the derivative at each point gives you the slope of the function. Okay, and here you have a point which is like this, like a saddle point, we call it. Like it looks like a saddle almost. And then this point has a derivative which is equal to 0. But this is not local minimum, right? You can easily see that. We have to have the second order to make sure that we're not talking about these points, and we're talking only about these points where the first order or the slope is equal to 0, the gradient is equal to 0, and you can see that the second derivative, if you take here, it is non-negative. So this is the necessary optimality condition. The first order says that the first derivative should be equal to 0. The second order, you can just remember it in this way. The first order talks about first derivative. The second order talks about first and second derivative. The first derivative at that point should be equal to 0. The second derivative at that point should be non-negative. Okay? So you can see here we're talking about the point. So means point that if the second derivative is strictly positive, doesn't mean that the graph should be convex if that's for all points. But no, we are not talking about all points. We're talking about some points called x bar. Does it make sense? At that point, if the first derivative is equal to 0, the second derivative is non-negative, then we call it a local minimum. Does it make sense? Is it clear? So if all points from the second derivative are positive, then it is convex. Yes, we'll come to that one. Yes, but now we're just talking about the point, because in the example that I showed you here, this example, clearly you can see that this is not a convex function, right? And for a local minimum, we don't need the function to become convex. Okay? Good? You're all good? Fantastic. Now, so these two are the first, these are the necessary optimality condition. And then we introduce this set, which is X, set of all local minima. This is independent from X1, O1, O2, O3 that we are writing is just something that we have as the local minima, okay? And then we wrote this one. We said that based on the first order necessary optimality condition, we can write the set of all points that make the first derivative equal to 0. All points that make the first derivative equal to 0. We know from this one, the examples that I showed you, it might be a saddle point, for instance, that I showed you, and it's not local minima. Therefore, local minima, and we know from the second order necessary optimality condition that the second derivative should be also non-negative. We know that this one is a subset of this one. That's why we drew it like this, that x1 is local, and this is only all different x that you could find that make the first derivative equal to 0. Is it sensible? Is it understandable? I think it should be clear now, right? Based on the examples that I showed you. Now, in the next step, we introduced O2. We said that we have these points, that we have the first derivative equal to 0, the second derivative is non-negative. This is O2. O2 contains all local minimum. We're looking for the global optimum here. We said that at the next one, we have the sufficient optimality condition where the second derivative should be strictly positive, strictly positive. In this way, what we will have here, this becomes essentially a local minimum for sure, which gives us this point inside of X. Okay. If it's not clear, we'll go through them in the workshop. Then when I draw them on the board, it becomes clearer. What do you mean by both of them? These two? For all three, what we have is it is strictly positive with the other one we have greater than or equal. It is non-negative. So strictly positive versus non-negative. So non-negative means that it can be, it's like what I said, the mug has a sharp bottom versus you have the real mug which is a flat bottom. That's the difference. Okay. Now let me finish this. As I said, if it is not clear, we'll get back to this in the workshop. Yes. So O3 is our global minimum. Now, if we have convex function, remember that this is something that if we know we do that, or if it is the case, we know that we are looking for this or that. So what happens if the function that we have is convex? Suppose that f is a convex and differentiable at x bar at some points. Then x bar is the global minimum if and only if the first, essentially, when the first derivative is equal to 0. So if I just draw this, we know that this is a convex function, right? And if it is the convex function, this is what this is the reason that we learn convexity of the function. So if we know that a function is convex, we know that whenever the gradient is equal to 0, which is the slope of the function at this point, which means that the first derivative for this point is equal to 0, then the function, the point that we have, is our global optima. That's the case for the concave function. If it is a concave function, and we know that, because when it is convex, as you said, the second derivative is non-negative or strictly positive, or non-positive or strictly negative. If we know that, the point that we find, which makes the gradient equal to 0, is our global optimum, because we are sure that the shape of the convex is in a way that if you have this point, it can't become the local minimum, and it is the global optimum of the model. So if we know that, if the function is differentiable, first of all, it is convex at some point x bar, that's the global minima if and only if the first derivative for that specific point is equal to 0. I have to change in the slides for all of them, it should be x bars, because we're talking about this specific point. So what we will have here is local minimum and global minimum will be the same, and it is the global optimum of the model. Whereas in the previous one, we had x as the set of the local minimum and O1 as the set of global minimum points. If it is convex, the local and global minimums becomes the same. And this is the case that we discussed, that all global optimums are local optima, but the other way around doesn't work unless the function is a convex function. So local minima becomes global minima is always local minima. For a concave function, local maxima becomes global maxima always is a local maxima. Just get rid of them. So this is what we have. X becomes O1, and this is only because our function is a convex function. Because our function is a convex function. Okay. Necessary and sufficient optimality conditions. So this is what we have. Is there a local minima that does not satisfy second order condition? What do you think? Remember second order condition that we have? Is there any local minima that does not satisfy second order sufficient condition? If we go back to a local minima that doesn't satisfy second order necessary optimality condition, says that if f is twice differentiable, x bar is a local minima. If x is local minima, then the first derivative is equal to 0 and the second derivative is non-negative. Now the question here is there a local minima that does not satisfy second order condition? What do you think about this? Think about it. I won't answer it. It should be y equal to n. What do you mean? Maybe if x lies in negative region. Not really. Think about this. I will tell you, yes, there are points. Consider the function fx being x to the power 4. Okay? Think about this onto the workshop. See how it works, because it might be a bit, digesting might take a bit of time. Local minima that does not satisfy the second order sufficient condition. Second order condition says if x is a local minima, then the first derivative is equal to 0 and the second derivative should be non-negative. Okay? Now consider f of x being x to the power 4 and see how the answer to this becomes 1 for this specific example. The second question that I have here, this slide, is there a solution that satisfies necessary condition but is not a local minima? Necessary condition, first order necessary condition, is that the first derivative is equal to 0. I already answered this question, that we may have f of x being x cubed, and then at point equal x equal to 0, this can happen, that it satisfies the condition, but it's not a local minima. That's why we have these different sets. Think about this, two questions. For the first one, as I said, it is f of x being x squared, and the second one is x cubed. And for both of them, x being equal to 0. Think about them until the workshop, and in the workshop, I'm pretty sure that it becomes much easier. Just to show you an example of the questions that you may encounter in this as a part of this module for this topic, or like this. So I want you to know the reasoning and the theorem behind it, but this is what I expect you to do. We want to minimize this function. As you can see here, we want to minimize this function, which is x squared minus 4x plus 3. And x has no conditions imposed on it. So it is super simple, right? So what you do is essentially you take the first derivative, which is 2f prime is 2x minus 4. We want the first derivative to become equal to 0 to get all candidates that can become the local minimum. Among them, some become global optimum. So 2x minus 4 is equal to 0. X becomes equal to 2. So this is a candidate that we have. It may not be local minimum. It may be. It may not be the global optimum. It may be. Now we're going to test the rest. This is the first order necessary optimality condition. The second order necessary optimality condition says that the second derivative should be non-negative. For this case, it becomes 2. Is it non-negative? Yes. It is non-negative. Yes. So this is a local minimum. Okay? Now, if you check the sufficient optimality condition, it is strictly positive, so it becomes our global optimum at the same time. The value of fx, just plug this to the main function that you have f of 2, which gives us -1. So the point that we have, it is one-dimensional space, right? So it is 2 and 1, the point that we have. Before I stop here, a few points. As I said, this is the sort of like problem that I expect you to be able to solve. As I said, I want you to know the theorem behind what is like first order optimality condition, necessary and sufficient optimality conditions. Also, some of you ask me, sorry, -1, yes, yeah, of course. It's 2 and -1, the point. Thank you. I was going to say, oh yes, some of you asked me during the workshop last week, specifically when we wanted to take the derivatives. We talked about first derivative, second derivatives. You asked me about the functions with multiple variables. Our focus on this in this module is only univariate function. So we only have one decision variable. Because if you have more than one decision variable, you have x1 and x2, then the derivative or the second derivative, it becomes different, that you will have Hessian matrix and those stuff that I don't want to cover at the part of this module. Okay, so our focus is only on univariate functions where we have only one decision variable first. The second one is I want you to know the first and second order necessary and sufficient optimality conditions. And in terms of optimization, this is an example of optimization, nonlinear optimization problems that we solve in this module. That said, I'm going to stop here. If you have any questions, feel free to stay and ask me. As I said, it might be easier to just show them on the board in the workshop, the conditions and those stuff, for you to understand it better. So if you have some doubt at this point, don't worry about that. We will resolve them during the workshop. Feel free to leave. If you have any questions, just stay. I'll see some of you today, tomorrow, and other days. Okay? See you for now. For a local minimum to become a global minimum, we need a function to become a convex function. So I'll have this one here. Remember our discussions last week for the convexity. What I had was this function clearly is not a convex function, right? It is neither convex nor concave function. And this is a local minimum. This is also, it's not local. I just wanted to have this one local, but it has a gradient equal to 0. It has a gradient equal to 0. This has a gradient equal to 0. This is a local minimum. This is global minimum. And this one is not local, neither local or global. If the function that we have is a convex function, we know that this is the local minimum. At the same time, this is a global minimum as well. Right? It is a global minimum as well. For this to happen, we have the sufficient condition, which says that the first derivative is equal to 0. The second derivative is strictly positive. In this case, we have global minimum point. So the second derivative tells us about what direction the curve bends as it up and down. Yes. So then it is positive. We can say it is, okay. You just need to be careful about this. What we have here, there are points here, okay? This function, obviously not convex, not concave, right? You see that. You obviously see that. But you can see here that the second derivative of this function, fx, for x, is greater than or equal to 0 for some x's, right? For some values of x we can find, second derivative being non-negative. This is unlike this one. This one is the second derivative is always non-negative for all x in Rn. Okay, you have to be careful about this. So it's not the second derivative at that point, those points, but the whole domain of the decision variable. If it is non-negative, then the function is convex. Otherwise, if you consider some points in which the second derivative is non-negative, that function for that specific domain is, for that domain, I mean not domain, for that specific range for the decision variables, it is convex. But you can see the function itself is not. So what I'm talking about here is that if the function has a second derivative which is non-negative for all points in the domain of the decision variable, then the function is convex. Then the local minima is the global minima at the same time. Okay, you got it, Amanda? What is the actual difference between necessary and sufficient condition? So necessary condition says that it is greater than or equal to 0, but the sufficient condition says that it is strictly positive, as you said. Yes, when it is, the second derivative is strictly positive, and we know that it is valid for all different values in the domain of the decision variable. What do you mean by all values within the domain, as in real numbers? If it is unrestricted, unconstrained, yes, unconstrained. So let me just erase the slide. So what I'm saying is this one. There are two functions that we have, okay? This is clearly not convex, right? It's not a convex function. It's not convex, not concave. For this one, let's say this point is x equal to 3. For x in like 1 to, let's say, 5, if x is between 1 and 5 for this specific function, the second derivative of, let's say, let's call it x bar, okay? If x bar is within 1 to 5, the second derivative is greater than or equal to 0. However, this function is not convex. The other example that I have is this one. This is the minimum that we have. Now, d of d2, the second derivative of fx over dx is non-negative or strictly positive, depending on the sharp or being flat, for all x in R2. This two-dimensional space, all R's. Okay? So you see the differences. This one is a local minimum, but this one is a global minimum. I know this one because this is a convex function. How I know this is a convex function? Because the second derivative for all different values of x within the domain of decision variable are non-negative. Was it? Yes, yes. I mean, I'll have to check that. Let me go back to the slide. You mean this one, right? They say that it is a global optimum. I have to check to see if this is a convex function or not for all values. I didn't check that. It is, right? It is 2. So yes, I mean, the second derivative is equal to 2. So no matter what is the value of x, it is a convex function. So that's the global minimum. Okay. Any other questions? So we can find out if a function is concave or convex by checking the second derivative. Yes. Yes, of course. Or you can use the definition as well. The second derivative is equal to 0 as a critical point. How do we? You can't guarantee that. So when it is equal to 0 for a specific point, you mean, right? You can't guarantee that if it is minimum or maximum or something like a linear function, for instance, right? Linear function, the second derivative is equal to 0. So you can't say anything like that. And depending on the function that you have, when it is equal to 0, that's why when we have greater than or equal to 0, we call it like convex. When it is greater than 0, strictly positive, call it the strictly convex function. When it is equal to 0, for some points, you can't guarantee if it is a minimum or maximum. So we can function is going to so if here is the second derivative is greater than it is convex. Greater than or equal, less than or equal. So equality is also included. When it is greater than or equality, this convex function, when it is greater than 0, as you wrote, it becomes strictly convex. Okay. Okay, and when can we find if it is not a convex? If it's not the case, so you may have, so when you say that the second derivative is equal greater than 0, it's greater than 0 for all points. For instance, x cubed, if you take the second derivative, it becomes 6x. It's not positive, it's not negative, it's not non-negative, it's not non-positive. Depending on the value of x, it might be positive or negative. In this case, it is neither convex or concave. Any other questions? Great stuff. Good discussions. I presume you don't have any other questions, so I'm going to stop recording first.